So we're working on some, actually I don't know what these are called, but here,
Matrices?
actually it's word, huh?
Matrices?
No, they're like logs and like
Logs and exponentials.
yeah, kind of.
Okay. Logs and exponentials go together like ham and eggs.
Yeah, and we're also doing like natural log and
That's just another kind of log.
yeah, okay.
Now, most of that you can probably verbalize.
Well, the stuff that we're doing now is kind of word problems. It's like, here I'll give an example. It's like a cup of coffee has cooled from 92 degrees Celsius to 50 degrees Celsius after 12 minutes in a room at 22 degrees Celsius. How long will the cup take to cool to 30 degrees Celsius?
Well, there's a formula called Newton's law of cooling, which you have to plug all these things into. Now, I don't have it memorized, but I can probably look it up. Do you have it memorized?
Well, the way that we were doing it in class is like we would do, say for this one we would do like 92 equals 22 because that's the room temperature.
Here, I got it. Just a second. Everything in math begins with an equation.
Yeah.
And that's what you want here, is you want Newton's law of cooling. One second. Well, hold on. I looked it up. Thought I was looking on the right page. One second.
Well, we have a formula for doing it, and it's, hold on, let me see.
Well, let's make sure it's the same thing. 343 on my book. All right. Here's what it says. U of t equals the temperature plus U sub 0 minus t times e to the kt.
Yeah, that's the formula we're using.
Okay, where k is less than 0.
Mm-hmm.
And T is the constant temperature. So, let's see, U of T equals, T is the constant temperature, which is that one, correct?
The constant temperature in the room is actually 22 degrees.
Oh. What's this 20 degrees? Oh, it should have been 22?
Yeah, it should have been 22, I think.
Okay. So
here,
you
want me to read the thing to you again?
Yeah.
Okay, so I'll go slower, sorry. A cup of coffee has cooled from 92 degrees Celsius to 50 degrees Celsius after 12 minutes in a room at 22 degrees Celsius.
Okay.
How long will the cup take to cool to 30 degrees Celsius?
All right. So our equation is 22 plus the initial, that's what U sub 0 is.
Yeah.
Minus
50?
T is the constant temperature of a surrounding medium, yeah? all times e to the kt. Well, here's what's going to happen is what they're saying is that it's gone to 50. Okay, so I can say the following statement. 50 equals 22 plus 92 minus 50, or excuse me, 92 minus 22, my mistake, times e to the k, and they've told us that that takes 12 minutes. Okay, now if you look at that equation, there is only one variable, k, and we can solve for it. And once we do solve for it, then we'll know what k is, and we can find out how long it's going to take to get to 30 degrees. You with me?
Yeah.
Let's go through the math, because this requires logarithms to solve. So I end up with 50 equals 22 plus 70 e to the k12, where time is in minutes. Okay, and then I get 28 equals 70 e to the k12. And whenever you have your variable in an exponent, it's a log problem.
Yeah.
And furthermore, you got to isolate this. I cannot take the log of both sides until I isolate what I have circled there.
So do you either divide the 70 from both sides, or can you actually put the 70 into the k?
No, you need to divide the 70.
Okay.
Because that'll get rid of it, and that gives me e to the k12.
And then you can put that in log form.
And I want to use natural logs. This is one case where you definitely want to use natural logs, because the natural log of e is 1.
Yep.
So the right side of the equation is k12. So k is going to be equal to the natural log of 0.4, which is a negative number.
Divided by 12.
Divided by 12. So that's a negative number, and k should be negative. What do you get when you do natural log of 0.4 divided by 12?
Oh, I don't know. I don't have I don't have a scientific calculator to do that.
Okay, you should always have a calculator in front of you when we're doing sessions.
Oh, wait. I think I might have gone.
And I've got one, but it doesn't do any good for me to do it. You're the one that needs to know how to do it on your calculator.
I think I got it actually, and I got negative 3.401.
Okay, now that gives us the equation that we're looking for. Is that the final temperature equals the surrounding temperature plus 70 E times minus 3.401 T.
And now we're looking for the time it takes to cool the coffee to 30 degrees.
To 30. So we would have this. And then there's only one variable still in the exponent, so we're still going to have to use logs. But it's going to be a slightly different answer.
So 8 divided by...
Get it? Yeah, so 8 divided by 70 equals
0.11.
3. That was minus 3.401.
Wait, did you already do the natural? Oh, yeah, okay. Sorry.
In other words, the whole purpose of the first part of that problem was merely to solve for k.
Yeah.
K is different for every law of cooling. In other words, this particular stuff that was cooling off has a K of negative 3.401. So we go back to the original equation and we substitute negative 3.401 for k. Everything else becomes the same. And now again, I want to take the natural log of that.
8 divided by 70, right?
Well, when I take the natural log of the left side, I get that. I take the natural log of the right side, I get this.
Okay.
So t is going to be the natural log of 8 divided by 70, all divided by minus 3.401. That's a negative number. The logs of numbers less than 1 are always negative. Divided by a negative number, so time is positive, and that's what we want. What do we get for time? And it better be more than 12 minutes.
More than 12 minutes?
Well, notice that it took 12 minutes for it to go from 92 to 50.
Wait, coffee cup has cooled from 92 degrees to 50. Yeah, okay.
So to get all the way to 30, it better be more than 12. What do you get when you stick this in a calculator? Natural log of 8 over 70 divided by minus 3.401. And
yeah,
you put that in parentheses, otherwise you won't get the right answer.
divided by negative 3.401.
Yeah, and our answer is going to be in minutes.
I got something that seems wrong. I got 0.637.
Yeah, that is wrong. Hold on a second. Let me bring up Wolfram Alpha, and let me put that in there.
Because I was going to say that wouldn't make sense even with that, like, if you just look at it.
No, it's got to be longer than 12 minutes. So what do we got? We got natural log of 8 divided by 70. Got to have that in parentheses.
Yeah, that's what I did.
Divided by negative 3.041. Ah, 0.713. And that is the input. No, hold on, it isn't. It's the natural log. I don't think that matters. It's not going to matter. Yeah, no, they got it right down here. It's the log base E. So,
if anything,
what did we do wrong? Let's have a look. Alright, so the start of the problem, we knew that it went to 50 with a surrounding temperature of 22, an initial temperature of 92. So 50 equals 22 plus 70 e to the k12 with t being in minutes.
Wait, so hold on, let me get this straight. It's the natural log of 70 divided by 80, right? That's what we were doing.
No, it's natural log of 8 divided by 70.
8 divided by 7?
See what I got written on the left, circled?
Okay, yeah, that's okay.
It's a natural log of 8 over 70, which is a negative number, divided by minus 3.401. Now let's figure out what the natural log of 8 divided by 70 is. Obviously I got something wrong. Yeah, when I divide that number by 3, you sure that's what we had for 3? I think that's probably where our mistake is. We've got
Where?
k equals the natural log of 0.4 divided by 12. Let me put that into Wolfram Alpha.
Oh yeah, my calculator might be wrong.
Natural log of 4 divided by 12. No, 0.4, right?
Yeah. Yeah.
Natural log of 0.4 divided by 12.
Do you need the parentheses?
No, I shouldn't here. Yeah, that result is minus 0.076.
Hold on, what did I do wrong? Hold on, let me type this into my calculator again.
Make sure you take the natural log. You will need the parentheses only on the top. In other words, notice what it wrote. It's the natural log of 0.4 in the numerator, just 12 in the denominator. You're not taking the natural log of that ratio. You're taking the log of 0.4 in the numerator, dividing that whole thing by 12. So that's
yeah, I got that.
0.076. That's why it's important for you to do it in your calculator and not me.
Yeah.
Because that's the last mistake in the world you want to make, is where you don't get it right on your calculator.
Yeah, because I was doing that whole thing in parentheses, not just the 0.4.
0.0763.
So,
Alright, so that changes our equation considerably. That number there is going to be negative 0.0763, and so our answer is what? What's natural log of 8 over 70? That needs to be in parentheses.
yeah, and then divided by
negative 0.0763.
So I think I got 28.42.
Well, at least that makes sense.
Yeah, I'm not
gonna check your answers because I don't have my calculator in front of me for a good reason. I don't want it. I want you to come up with the answers on your calculator. Okay? And that answer makes sense. If it took 12 minutes to cool from 90 degrees to 50, or from 92 to 50,
Wait.
then went from 92 to 50 in 12 minutes. It's got to go all the way to 30. And its surrounding temperature is 22. So it would take longer than 12 minutes. And that's a perfectly reasonable answer, 28.42 minutes.
Hold on, I just did it again and I got 31.928.
What kind of calculator are you using, Simon?
I'm using my phone calculator. I don't have a actual graphing calculator or anything.
What kind of calculator are you going to use on the test?
Well, they supply calculators, which are nice, like TI-84s.
Okay. The TI-84 has a natural log button.
Yeah.
And it also has a common log button. So coming up with the natural log of 8 over 70 is your first step. Then divide all of that by minus 0.0763. Now, I can do it again on Wolfram Alpha, although I kind of feel like this is wasting our time. What is it? 8 divided by 70?
Yeah.
All divided by negative 0.0763.
Okay, no, I'm sorry, I'm just wasting time at this point.
28 minutes, 28.42 minutes.
Okay, so I was right the first time. Sorry, my calculator just switched up the answers and I don't know why.
Well, that's part of learning, though. In other words, I'm glad we discovered that. You would not have wanted to discover that after the test.
Oh, yeah.
So that's why I want you to do it on your calculator.
Okay.
Okay. What else do we got here?
Okay, so here we go. This is another one. A detective finds a murder victim at 9 a.m. The temperature of the body is measured at 90.3 degrees Fahrenheit. 1 hour later, the temperature of the body is 89.0 degrees Fahrenheit. The temperature of the room has been maintained at a constant 68.0 degrees Fahrenheit. Estimate the time the murder occurred. Hint, assume the living body is 98.6 degrees Fahrenheit. Okay.
All right. So we go back to our original equation. The current temperature is equal to the temperature of the medium.
So 68.
Well, let's write the general down first before you plug in. That is key. I mean, that's big. And I think that's important in all of math. Always start with the general equation. Now, let's plug in what we know. The temperature of the surrounding medium is what?
Temperature of the surrounding medium is 68 degrees Fahrenheit.
Okay. So, U of T equals 68.
Yeah.
Plus the initial,
which is 90.3.
Actually not.
Oh wait, no, the living body is 98.6.
Minus 68 times e to the kt. And here's what we know. We know that it went from 98.6 to 90.3 in some amount of time.
Mm-hmm.
Ooh. That's an interesting problem. Okay, let's go back a second. We went from 90.3 to 89 in some amount of time.
Yeah.
That's what we know is this.
It's 1 hour later. That's
right. That's going to be our t. So here's what we have is u of 1 is equal to surrounding plus the original, which is 90.3, minus the surrounding, all to the ek1. And this u of 1 is 89. So I've now got 89 equals 68 plus 22.3 e to the k. Solve for k. What do you get?
Minus 68. Minus 68. Hold on. Sorry, this is going to take me a minute. Equals. Okay, and then you divide that by 20. So k is going to equal the natural log of 21 divided by 2.3, I think.
22.3.
Yeah, 22.3. Sorry.
Okay.
So 21
That'd
over...
be a big difference, incidentally. If you make one decimal point, it's going to be like a factor of 100 in your answer.
Yeah. Okay, so, and then it's... Here, let me type this out correctly this time and not...
A negative number because it's the natural log of a number less than 1.
So it'd be natural log of 21, right?
No. No. It's natural log parentheses 21 divided by 22.3 end parentheses.
Divided by 22.3 end parentheses. And then should I put that all over...
No, not yet.
Oh, wait, no, that's what we're trying to find.
That's what we're solving for is k.
Okay, I got negative 0.0600.
Negative 0.06, okay. Now we know what K is, and we can go back and write our equation over here on the left. The temperature is going to equal the surrounding plus the starting 98.6 minus the surrounding all times e to the negative 0.06 t. And what we're wanting to know is how long it will take to go from 98.6 to 90.3. Correct? You want to know the time of death.
Yeah.
Death is what it started at. It's the time it takes from 90 to get from 98.6 to 90.3. That's how long it's going to take before the body died. So 90.3 goes over there. 68 plus the starting.
So 98.6.
And then e to the minus, we've solved for K. So there's our equation right there. And there's only one variable in that, T.
Yeah.
So we're going to be able to come up with a T, which will tell us how many hours passed between the living body and the dead body that was discovered at 9 a.m. So let's see. Let's come up with a number and see if it makes sense. We got 22.3 equals 30.6 e to the negative 0.06 t. So e to the negative 0.06 t equals 22.3 divided by 30.6. We're going to take the natural log of both sides, which gives us negative 0.06 t equals that natural log. So t is going to be that natural log divided by negative 0.06.
Okay, so the natural log of 22.3 divided by, what is it, 30.6? 30.6.
Yeah. Do that first. Make sure you get a negative number. In other
Equals,
words, a lot of times on this, especially on that calculator, it's real easy to make a mistake with your parentheses, as you saw. And so to avoid that, do it in pieces. Don't try to put all of that into the calculator at once. Not on a TI-84. If it was a TI-Inspire, then not so bad because it shows you exactly what you've put in.
Yeah.
But on the TI-84, it doesn't show you. So do that numerator first. Make sure you get a negative number.
Yeah, I did. Okay. And I think
that number by minus 0.06.
And I got... So this is going to be AM, right? It should be?
Now, give me what the time is.
Okay, so the time, I guess, would be 5:27?
Well, you didn't give me the answer. What's T?
So T, well, what I got when I did that natural log of, what, 22.3 over 30.6, and then I got the negative whatever number that was.
I don't care what that number is. Now take that number and divide it by negative 0.06.
And I got 5.273.
And that is in hours.
So that's what I was saying.
We solved for K based on T being 1 hour. Okay? So the time of death was 5 hours before we discovered the body.
Yeah, okay, so what is it? 9, so that would be 4... Yeah. It would be 3:30, 3:33 about.
You know, This problem is tough enough as it is. They had to give us a decimal answer. They couldn't have come up with a whole number for t. So we discovered the body at 9 a.m. So at 5.273 hours before 9 a.m. is the answer.
I think it is 3:33.
No, I don't think so. Well, figure out what 0.273 of an hour is.
Oh yeah, I didn't do that. It would be it'd be something like, I don't know.
Well, do it in your calculator. 0.273 times 60.
Okay. 0.273 times 60 equals 16.38, so then that would be
5 hours, 16 minutes. Prior to 9 a.m. That puts it back at 3:44, if I'm rounding off. a.m. Which is 3 hours and, which is 5 hours and 16 minutes before 9 a.m.
Yep, before 9.
We discovered the body. So the key things to understand on this problem is that based on Newton's law of cooling, that allows you to calculate K. Once you've calculated K, now you can go back and figure out how long it took to go from 98.6 to 90.3.
Okay.
And that's always kind of the process. In fact, not just with this problem. Whenever you see a problem that has a K in it, you can bet anything that your first step is to calculate that K. And it doesn't matter if it's a direct relationship or not. In other words, if I say y varies directly with x, the first thing I'm going to have to do is calculate k. And they'll say, when, hold on, you've had these kind, I'm sure, also, haven't you?
The y equals kx?
Well, no. You've had problems where it says y varies directly with x or y varies inversely with x.
Yes,
and
I think.
I'll say when x equals 3, y equals 12.
Yeah, I have had problems like that.
Okay, well, if we plug in the y and the x, we solve k equals 4. Now, the specific equation is y equal 4x. Now they would say, what is y when x equals 1? Well, now you can figure it out. Y would be
4.
So the first step is always to solve for k whenever you have one of those kind of an equations, whether it's exponential or not. In other words, even if I have principal equals e to the kt, which is, if I have this, the current amount equals the original principal times e to the kt. If you have continuous growth, when you have a problem like that, you can bet they're going to give you enough information to solve for k. And then once you solve for k, you have the specific equation for that principal or for that model. Then you can answer their next question. But almost every problem that has a k in the original formula, that's the first thing you're going to have to solve for. All right. What else?
So hopefully we can squeeze in one more problem. So suppose a corpse was, it's another dead problem. Suppose that a corpse was discovered in a motel room at midnight and its temperature was 80 degrees Fahrenheit. The temperature of the room is kept at a constant 60 degrees Fahrenheit. 2 hours later, the temperature of the corpse, dropped to 75 degrees Fahrenheit. Find the time of death.
Okay? Same exact problem, different numbers. Start with the original equation, which is what?
Which is going to be, so it's ut equals t plus u0 minus t e to the negative kt.
Yeah, and this is something that's always kind of puzzled me. So why they put the negative sign in there? I don't get it. I never have. But it doesn't matter whether you put the negative sign in there or not. If I leave it off, then k is going to end up being negative. If I put it in, I'll end up with the same k, but it'll be positive. So it won't matter. I myself prefer to leave k like that without the negative sign, because the negative sign takes care of itself. And I honestly don't quite know. It might just be convention.
Okay.
As to why some books have a negative k and others just use a k. Alright, so what they're saying is that it went from something to 75. Surrounding temperature is 60. The initial temperature was 80, so it went from 80 to 75. In 2 hours. Notice how the only variable there is k.
Yeah. So it's going to be...
K is going to be 15 divided by 20 equals e to the 2k. So we're going to end up with the natural log of 3/4 equals 2k. So we get k equals the natural log of 3/4 divided by 2. Notice that is not the natural log of 3/4 divided by the natural log of 2. Do that first in your calculator, get a negative number.
Divided by 2.
And then divide it by 2.
And I got negative 0.143.
So that's k. Now we go back to the original problem, the original formula, where we now have k. Let me just plug it in up here. And notice I'm going to plug in the negative that you got, because it always turns out to be negative. Okay. Now, let's erase all of this. That's the proper formula for this body. In other words, k might be different for different bodies, different size bodies, would cool off at a different rate.
Yeah.
If I had they don't tell us the size body. This could be a 400-pound man, or it could be a 100-pound woman. Well, each of those bodies would produce a different k. So this k is this dead body only.
So
now, you want to know how long it took from its 98.6 to get to 80.
Yeah.
So we're going to 80. Surrounding is 70. Plus the original, the living body is 98.6 minus the surrounding. E to the minus 0.143t. Again, only one variable in that, t. The key is we're going from this temperature to that temperature. Question is, how long does it take?
So that's what?
Living body to 80 degrees. And when he died, he was not at 80 degrees. He was at 98.6.
Yeah, and then, so that's it, 38.6.
The K applies to that person only. So I can figure out how long it took to get from 98.6 to 80 as long as the surrounding room was still at 60. So that gives me 20 divided, and I'm taking a few shortcuts here just because
Yeah.
time's running out,
Mm-hmm.
equals minus 0.143t and natural log of that. So we got the natural log of that divided by minus 0.143 is our time that it took to go from 98.6 to 80.
And that time is 4.59 hours.
Okay, so now tell me, what time did he die?
Hold on, 4.59 hours.
Gonna
So you multiply 0.59 by 60, right?
correct?
No. Yeah, okay, by 60, and that equals 35.
So
it's
that means that it took 4 hours and 35 minutes.
So
Now you can work backwards.
so it's midnight,
Minus.
and so
backwards.
it's gonna be
What's 4 hours prior to midnight?
4 hours prior to midnight. That's 8, so it's gonna be 7:25.
You got it.
7:25
p.m.
p.m.
4.5 hours prior to the discovery of the body.
There it is.
Cool. Darn, feel like CSI here.
Oh yeah.
Who knew that you could use this Newton's law of cooling to find out when a dead body died? So all you got to do is wait a couple hours. In other words, let's say you discover the dead body at 8 or at midnight. If you want to find out when it died, you got to wait a couple hours to see what its next temperature is.
And then you can
to solve for K. Then you can work backwards and figure out when it was at 98.6. So it's kind of cool when you think about it. In other words, they wouldn't really be able to calculate anything at midnight.
Yeah.
They wouldn't know enough. They have to figure out how much the body cools off in some period of time after midnight. And you'd want
that's why they waited 2 hours.
a reasonable amount of time for accuracy. You wouldn't want to wait till just 12:01. And so they wait a couple hours, cools off 5 degrees, and that allows them to figure out everything else.
Yeah, that's pretty funny.
All right, Simon. I have a 4 o'clock, so I got to run.
Yeah, I don't. Okay, well.
I'll talk to you next time.
Okay, take it easy.
All right, bye-bye.